So, we will continue a bit into a discussion of the improper integral where we have left. We will tell you about some more concepts. For example, just now we are going to discuss what is called the Cauchy principal value. This due to the mathematician Cauchy, a French mathematician. So, the modern version of calculus that we see is largely due to Augustin Louis Cauchy, and he has a very typical way of looking at an integral which is of the form like this. So, what do you mean by the convergence of this integral? How do you define? That is again a question, right. So, somebody would say, okay, I know about how to handle 0 to infinity or a to infinity, and so minus infinity to a, 0, a is 0 standardized, for example. So, maybe I would say, okay, let me think that I can write the integral, if it is at all convergent, into two parts. So, each of them are improper integrals, and if I can sum them up, I mean if I can show that each of them has a finite value, then the integral must have a finite value. That would be the basic intuition. So, what would happen, what Cauchy said, that why can't we look at it in a different way? So, why do not I now replace minus infinity and plus infinity and integrate by the same, integrate this function? That is okay. You say, okay, there is a function, okay, defined like this, and goes into minus infinity and to plus infinity and minus infinity. So, here you take some minus p and here you take some q. So, basically you have to then write infinity to minus infinity f(x) dx. So, is this a nice way to do it? That is what was Cauchy's question, minus q to p where limit p goes to infinity and q also goes to infinity. So, here you are taking limit of the two ends, right. Sorry, here minus p to q. So, minus p to q. So, here we are going to having two limits. So, basically when you write down the integral, both sides you are taking to infinity. Whether this makes sense or does this make sense, that is the question. Because what Cauchy said, okay, taking two limits can be very pathetic. So, we can more or less have a symmetry and say we will write it like this, instead of q we will take p here and we will put here as p and just take p going to infinity. Now, if this value exists, then we say that the integral exists in the Cauchy principal value sense or CPV. A function existing in the Cauchy principal value sense may not exist in this sense. So, Cauchy principal value sense is a very different way of looking at the integral. So, basically when you have minus infinity to plus infinity, then all integrals of this form must exist. It does not matter whether you have put it 0 here or some number a, it does not matter. So, ultimately these integrals should just exist. But what can happen, that this integral exists minus p to plus p, but when you separate them up and come from one end to 0 and 0 to other end, it does not simply exist. An example which is given in Goldberg's book is very, it is one of the most elegant books on mathematical analysis. It is called Real Analysis by Goldberg, but you need not bother to read this at this moment. So, what I am doing is, as we Samuel Goldberg, S. Goldberg. So, as we move gradually up the ladder, we are going from calculus into more in-depthly analyzing the issues. So, we are getting gradually into the domain of real analysis. It does not mean that we are not going to do computations, etc. We will do it. For example, if you look into this integral, now you separate them, look at these two parts individually. Does it exist finitely? And so, if you work them out in the standard way, that taking limit a tends to infinity 0 to a 1 plus x by 1 plus x squared dx, then you will quickly realize that this will really not work, because I can actually, for example, if you write this as limit of a tends to infinity 0 to a, and you can separately work this out. So, what would this integral give me? So, what would this integral give me? The first one. The first one is 0 to a 1 by 1 plus x square dx. This is an elementary thing to know, that this is nothing but tan inverse x, and that we are evaluating from 0 to a. So, it is tan inverse a. The next one, so you substitute 1 plus x square as t, right. So, when you substitute 1 plus x square as t, you will have 2x dx is equal to dt. So, this would be equal to half of x dt by t, and the limit would be from, when x is 0 the limit is 1, when x is a the limit is 1 plus a square. So, this will be nothing but half log of 1 plus a square. Of course, this is defined, log 1 is 0. So, now this simply means that I have here tan inverse of a plus half log of 1 plus a square. So, as a goes to infinity, if I take the limit of this as a goes to infinity, 1 plus a square is also going larger and larger, and the log value is going towards infinity. Tan inverse a, as you, if you draw the graph of the tangent, and if you look at tan inverse a opposite, if tan inverse a goes to infinity, that is as y goes to infinity basically, on the a goes to infinity, tan inverse a also goes to infinity. So, these two are going to be becoming infinite. So, this limit is plus infinity. So, if one of them does not exist, the other obviously has, if you do not even calculate, does not have any problem. So, you just calculate one of them. Now, interestingly enough, let me try to calculate this one. So, now what I will do, I will calculate the Cauchy principal value. So, now I will have say minus A to A or minus P to P if you want the same formulation, minus P to P 1 plus x divided by 1 plus x square. How do I calculate this basically? Now, what I am supposed to do here, this is Cauchy's idea that suppose if I can calculate this. So, one might say okay, here you might just go into a problem because tan inverse P you take to infinity and here you will have the same thing P square and then there will be a something log of you will have tan inverse for one part you will have tan inverse P minus tan inverse minus P. So, that thing might just get complicated. So, let us look at this situation in a slightly different way and let us see what we can do with this. What we do is take this function, this one, this. So, instead of minus P to plus P, so minus P to plus P, we will make it slightly simpler in the calculation. So, I will write minus P to some S, okay. Sorry, minus P to 0. So, what I am doing, I am instead of breaking up the interval as minus infinity to 0 and plus infinity to 0 to plus infinity and in trying to evaluate the limits separately, I am going to break up this integral into two parts, because that is the easy way to do this integral. Even if I have the system, even if it is a finite integral, I can do it separately, right, minus P to 0, 0 to minus P. So, 1 plus x 1 plus x square plus 0 to P 1 plus x 1 plus x square dx. So, what I am trying to do here is that now I will compute this and take P as P going to infinity. I will compute this integral, each of the separate integral and see that P is going to infinity. Now, I can simplify this a bit. So, if I put x equal to minus u substitute in the first part 1 means this part, and x equal to you substitute in this part. So, what would happen? Then it will have minus P to P 1 plus x 1 plus x square would become 0 to P 1 plus u by 1 plus u square du, right? 1 x is equal to 1 minus u, this will become 1 minus u by d square, and this will remain. Putting x equal to u, it will become just the same thing. So, here if you put x equal to minus u, dx will be minus du. So, minus would come here. So, 1 minus u 1 plus u square du. So, when x is equal to minus p, x is equal to minus p, u becomes p, and when it is 0 it remains 0. Since it is a minus 1, it sign the integral positions of the integrating points, that is the end points, they change, the interval sweeps. So, it becomes 0 to p. So, now if you add them up, so what will you get? You will get 1 plus 1 2 u will cancel. So, you will get 2 0 to p. So, this integral has now come down to this nice little form. Now, if I take limit p tends to infinity minus p to p 1 plus x square dx. So, this is actually the Cauchy principal value CPV. So, then what I am trying to now write, this is same as 2 times limit 0 to p tends to infinity 1 by 1 plus u square du. So, basically it is 2 into tan inverse infinity, actually I should not write that tan inverse infinity. So, essentially it means 2 into pi by 2. So, the cancels and answer comes to pi. So, you see the limit exists finitely, and hence the Cauchy, in the Cauchy principal value sense, this integral has a value, though it does not have a value in the standard sense. So, this is a very interesting approach, but it is not, I think most people will not even bother, modern text would not even talk about, but that is also in one way. So, in those days convergence was a very important issue in convergence of integrals, and people wanted to make even not so good looking nice integrals. They wanted to design ways by which they should have value, just like people wanted to increase the number of functions which could be integrated. Now, we are going to talk about how to test for convergence and divergence. So, for example, we will start investigating the convergence of an important integral, right, an important. So, we will tell now, we will discuss from the standard text which I have already mentioned in the beginning, Thomas and Finney, or Thomas's calculus, which is very standard. So, we are going to integrate, let us try to use, you know that if I take the indefinite integral of this integral, just 0 to integral of e to the power minus x square dx, it does not make sense because there is no function whose derivative is this. But can I calculate this? Does this integral have a value? Is it finite? That is, of course, is the question. Now, I will give you a slightly puzzle, a game to play a little bit. So, I conjecture two things. I say, okay, alpha is positive. And I say that, okay, this is something I would like you to, I give you a quiz question, that is, I say that it is, I say, okay, maybe many of you who are preparing for JEE or some other examinations or whatever you might tell me, might like this sort of questions, MCQ. So, I give you two set of questions, and you really have to answer to me without doing integration, what is the correct one. How would I really think about it? Suppose I am lucky enough and I can draw graphs of functions. See, always understand e to the power minus alpha x square's graph is not the graph of e to the power x. one has to understand this very fundamental fact. Obviously, if I put x equal to 0, it will become e to the power minus alpha and so forth. So, the question would be, how do you guess what would be the right answer? So, to guess what is the right answer, let me try out the following. So, let me tell you, if you draw the graph, you take any software like Mathematica or Maple, or if you have an access to, of course, I am sure many people who are watching this program does not have an access to. Just try your calculator and try, nowadays they have the exponential value in your this math calculators, and so you can just try out and draw some few points and try to extrapolate actually what should be the form. So, usually it will be a form like this. So, at x equal to 0, this is alpha. So, alpha's value is this. Sorry, x equal to 0, I am making a mistake again. X equal to 0, it will be 1. Now, what would be this would be the usually so it will become, so at x equal to 1, it is e to the power minus alpha and this functional value, and x equal to minus 1 also it is e to the power minus alpha. So, once you know this, that plus and minus 1, it has a value, it has a symmetric value, and then you try to know the nature. If you take this function phi x and say take x positive, and let us try to take the derivative of this. So, let us try to take the derivative of this, what would happen? So, phi dash x is equal to minus alpha 2x e to the power minus alpha x square. So, this is always a positive quantity, but this is not. For x positive, this is strictly less than 0. So, it is a decreasing function. Similarly, when x is negative, it is, so phi dash x is positive if x is strictly less than 0. So, it is natural that starting from the point 0, this graph would fall down. So, what would happen when if I now increase the value of alpha, I always have to keep at x equal to 0, it would be 1. So, this length cannot be changed. So, what I am supposed to do now, if I change the value of alpha, increase it, the graph would become sharper like this. The more increase I do of alpha, no sorry, my drawing might be very bad, the more sharper the graph becomes and the area under the curve decreases. So, as alpha tends to infinity, the area under the curve is decreasing. So, area under the curve is now decreasing, but what is this product phi alpha? So, area under the curve finally goes towards 0 as alpha would increase. Now, phi alpha means as alpha increasing, this is becoming bigger and bigger. So, this can never represent the area. So, 0 minus infinity to plus infinity e to the power minus alpha x square dx is root over pi by alpha. So, minus infinity to plus infinity e to the power minus x square dx is equal to root pi. I will tell you tomorrow a bit more about the computation of integrals and why, how you do it. So, this is one way that you actually do it, not one way, this is a way you can argue things out. I will show you ways by which you can actually compute these integrals without actually computing them. See, tomorrow we will spend some time talking about some interesting integrals, because it is not always about applications. Mathematics is also sometimes about mathematics, and what I am going to tell you tomorrow would actually help you in doing good computations. You will try to compute integrals without actually computing them. We will not compute them, but we will argue by looking at the structure of the function and the curves, etc., and we will actually get to their correct value. So, that will be a part of the training also. It is a so now we will go back to the more mathematical question of how do I, what is the, whether this is there, which means I am asking whether this is finite, which means I am asking whether limit now it might be slightly confusing, okay, looks slightly difficult, can't do much about it, but let me tell you, you can look at the whole thing in a very simple way. Now, that is why knowing graphs are so important. So, this is your one for, I am just drawing the graph, okay, this is your graph. So, this is 0 and this is 1. Now, what happens is the following, that you now you observe if I take up to 1, I will tell you why I am doing up to 1. The reason is follows. At x equal to 0, e to the power minus x is also 1, and the e to the power minus x's graph comes in like this. So, e to the power minus x after 1 actually goes above this graph. So, then it makes a much more easy for me to evaluate, look at the nature of this integral by the comparison test that we had learnt in the last class, that you can actually now compare them, because e to the power minus x is a thing where we have it is an elementary integral, right. So, you can actually have a derivative, you have a antiderivative. Now, this part which is 0 to 1, you see e to the power minus x square is a finite continuous function, and maybe you are not able to calculate the value just like that. We can obviously calculate it numerically, which will be one of the topics of tomorrow, numerical calculations. So, you see here this area is finite. So, basically if I want to look at this, I will look at it in this way. So, this I already know as finite, plus I will look into this, sorry. So, now let me look into this integration. So, you again know from the graph that this is nothing but so what is this? E to the power, what is this integral? So, it will be it will be e to the power 1 minus e to the power minus b, that would be the answer. Now, as b tends to infinity, this, sorry, e to the power, sorry, e to the power minus 1, thank you. So, it will be actually e to the power minus e to the power minus b minus e to the power minus 1. So, that will be minus and minus is plus, so e to the power minus 1. So, as b tends to infinity, e to the power minus 1 is not affected because it does not depend on b. Here e to the power, as b tends to infinity, e to the power minus x goes towards 0. This is a graph actually, and this, I think the graph is not so, it should be like this actually, it should come like this. This way. So, here all this is also going down, but it is going much towards 0 much faster to the minus. So, what would happen? Then integral 1 to b e to the power minus x 1 to infinity e to the power minus x dx is equal to e to the power minus 1. That is the answer. So, which means that 0 to infinity e to the power minus x square dx is some finite quantity, is actually less than some finite quantity plus e to the power minus 1, because e to the minus x square 1 to b dx is less than equal to this. So, when you write the limit, they will remain to be less than equal to. So, hence this integral is actually convergent. So, it was meaningful for us to discuss all this stuff. So, I will show you how just without doing actual calculation you will actually solve, you will get the answer root pi by alpha. We will do it tomorrow. Now, there is another test apart from this comparison test of showing that f x is less than or equal to g x, and if you integral 0 to infinity g x is finite, then f x is also finite. There is something called a limit comparison test. So, this is something also important. So, the limit comparison test says the following. So, I am writing the statement from Thomas and Finney or Thomas's calculus, but it is a standard result and find in too many books on analysis. So, it is limit. So, you have two functions f and g, right, and you do not know whether f x and g x what is their nature. So, I will have two functions. So, here I will have f x and g x are positive functions on say some a to infinity, okay, and say and limit f x by g x as x tends to infinity, what is their behavior. So, the limit should be a non-zero limit and a finite limit. So, limit as x tends to infinity should be L, and if then integral a to infinity f x dx and integral a to infinity g x dx converges and diverges together. Okay, it converges and diverges together. So, I will just give you one example and before I end the course. So, if one of them converges, the other converges, if one of them diverges, the other diverges, that is it, that is the meaning. So, let me take this one example and let us see what happens. So, this example is from Thomas and Finney, and they look into this function, this integration. So, your f x is equal to, obviously this is continuous on 1 to infinity and this after 1. So, this is a continuous function. What we know that somehow that x square is less than equal to 1 plus x square, because this is positive. So, 1 by 1 plus x square is less than equal to 1 by x square. So, by comparison test also you can prove that. But so 1 by x square could be my gx. Suppose I choose gx equal to 1 by x square. Here of course you know the comparison, but there suppose you do not even know, then okay, then you take fx by gx, I do not know whichever way you want to check, then it will become, maybe you, as the book suggests that we should change it, that is we should take this as fx and this as gx, this as gx and this as fx, okay, does not matter, maybe some easier computation. So, this will become what, 1 by x square. So, the limit x tends to infinity fx by gx is equal to 1, the answer is 1 here. But I know 1 to infinity 1 by x square converges, so 1 to infinity this also converges. So, this actually does not really require the limit comparison test, but it has been done. But what requires the limit comparison test, here is an example, integral 1 to infinity so, in this case use the fact that 1 to infinity, which we have just done, e to the power minus x dx, which is equal to integral 1 to infinity 1 by e to the power x dx, this converges, this we have already done, this is e to the power minus 1, this answer. So, take this to be your fx, then 1 by e to the power x by 3 by e to the power x plus 5. So, obviously you can, here it is not so clear, because you can say that e to the power x is less than e to the power x plus 5. So, 1 by e to the power x plus 5 is less than 1 by, so but if I multiply by 3 on this side, I do not know how to compare now. So, this fx less than equal to gx, that approach which showed in the last lecture cannot be applied here. So, here we really have to take the limit. So, limit as, I will not do the limit operation, I will just write the answer, so that you can figure out the limit yourself. Limit as x tends to infinity is equal to, so is 1/3 actually. So, then it is in that range. So, because already we know that this integral converges, means this is finite, and hence or this integral is also finite. So, with this we end today's lecture here, and tomorrow we will start by telling you how to compute which is the last 2 lectures for the 6th week is left, and the 7th and 8th week would be some few applications of integrals, and then going on more into sequence series, power series, and all sorts of things like that, and so of Taylor series and how those things come. So, what we are going to do, we are going to go back to differentiation again. So, and we will see the interplay between differentiation and integration. Tomorrow I will show you, for example, in applications I will show you, for example, how can you use integration, what you have learned, to show that pi is irrational. So, those sort of things, that is this is the proof by Ivan Neven. So, I will show those kind of things tomorrow. Tomorrow we will actually try to use integration in many ways, trying to compute integrals and doing other things, trying to see how numerically integrals are computed. So, obviously we can't do the numerics right away here, but we will show you the algorithms, how they are developed and all those things. So, this will be our discussion for tomorrow, and So, let me close today's discussion. It is already 43 minutes, 13 minutes is exceeded actually. So, I hope you had got some idea how doing the thing. So, improper integral discussion ends here. Thank you.